All right, here's what your study guide looks like for our quiz on thermodynamics or heat transfer. So, part of section 1 was to figure out what is temperature and what is heat. So, this one says define temperature in terms of kinetic energy. Look up your book's definition of temperature. Well, temperature is the average blank energy. It is average kinetic energy. If kinetic energy increases, what happens to your temperature? Well, temperature would increase. The more energy you have, the higher the temperature is going to be. And yes, temperature increases. Explain how a liquid thermometer measures temperature. You've probably seen the red liquid in thermometers before. What does the liquid do when it gets heated up or when it cools down? And so in this case, well, what happens to any molecules when they get heated up? Do they contract together or do they expand? Well, when things heat up, they want to expand. As they expand, same amount of molecules taking up more volume. That means the density decreases. When density decreases, it allows it to rise above the things that are more dense. So in this case, you have the molecules inside the thermometer, typically that liquid mercury. As it's heated up, it expands, and there's only one way for it to go, and that is up that tube in the thermometer. As it cools down, the mercury wants to get closer together. As it gets closer together, it sinks in the tube. So, as the mercury heats up, the expansion causes the liquid to rise. And that's what we'll say there. The next part, you don't have to do this part, converting the following temperatures as indicated. You can just Google them if you would like to, but 16 degrees Celsius in the Fahrenheit scale, what is 95 degrees Celsius? Or 95 degrees Fahrenheit on the Celsius scale. You can just look those up. You don't have to. I'm not going to dock you points if you don't do this part. Number 4, boiling and freezing points. Hint the information is in your notes. Fahrenheit, the freezing point, when it's cold outside, when is it going to start to snow? Typically around 32 degrees Fahrenheit is when things are going to freeze. Obviously, it could be warmer down here on the surface, maybe 34 degrees here on the surface, but up in the atmosphere, it's a few degrees colder, and that is why it is snowing. As you go up in our troposphere, that lower layer of our atmosphere, it gets colder. And so the freezing point in Fahrenheit would be 32 degrees. Boils at 212 degrees. In Celsius, it's a little bit easier to remember. Freezes at 0 degrees Celsius, and then it's going to boil at 100 degrees Celsius. And then the Kelvin scale. The freezing point would be 273 Kelvin. The boiling point is just 100 degrees higher than that because the Kelvin scale follows along with the Celsius scale. It's just always going to be 273 units higher. So if Celsius is 0, Kelvin is 273. If boiling at 100, well, what's 273 plus 100? That would be 373. At 0 Kelvin, all molecular motion stops. Since temperature is measuring how fast those molecules are moving, when they stop moving, you don't have temperature anymore. You don't have any energy left. We haven't actually achieved absolute 0 in the lab. Scientists have gotten very close to stopping molecular motion, but I don't think we're going to get there anytime soon. There's something called the unattainability principle, meaning every degree you get closer to absolute 0 becomes that much harder to get that next degree down. And looks like I accidentally erased that one there. So go back into this. The Kelvin scale starts at what and goes up? Well, absolute 0 is as low as it goes. So it starts at 0, or you could write absolute 0 and it goes up. There's no negatives in the Kelvin scale. Number 5, predict what will happen if a block of hot iron is placed in a glass of cool water. Well, that block of hot iron, well, what direction does heat transfer? Heat wants to move from hot or high energy to something that's cool. So in this case, the energy within that hot iron is going to get transferred to that cool water pretty quickly. And so you can say just that. The heat from the hot iron will transfer to the cool water. Until when? Is it just going to constantly transfer? Until the temperatures are equal. And if it's a better conductor, which typically iron is a good conductor, it's going to transfer that heat fairly efficiently, but it is going to water. Water isn't a great conductor. So that's what's happening there. Number 6, evaluate the following newspaper headline. Is it realistic? Explain. Scientists create a thermometer to measure temperatures below 0 Kelvin. Well, that would be, as some people say, just clickbait, because you cannot go below 0 Kelvin. You cannot go below 0 Kelvin. Zero Kelvin is absolute zero. You cannot go beyond that. Absolute zero is as low as we go. You can't stop motion more than just stopping it. There's no negative to it. So, number 7, explain why metal doors should not be built to keep heat from escaping or coming into your house, especially in a region where weather is hot. And now when I say metal doors, I should say pure metal doors. If it's only made of metal and you don't have any air gaps in there, no, it's not going to be a good thing to have for a door. It's going, in the summertime, that heat outside is going to transfer inside to your house more efficiently. And then in the wintertime, your warm air inside is going to allow itself outside because of that metal door. It's going to allow the heat to transfer right through it. And so why would you not want that pure metal door? Well, metal is a good conductor. And so it would allow heat to transfer easily, and you would not want that at your front door if you're trying to warm your house or cool your house. Oh, a little comma there. All right. Section 2. And some of you might be saying, well, I have a metal door at my house. Yeah, you might have a metal door. I have a metal door on my detached shed door. It's got metal on the outside, but then inside, sometimes they add a big layer of foam. Sometimes they add different air gaps, but they have to have some sort of insulator inside. Otherwise, it's not going to be an efficient way to keep the heat out or keep the heat inside your house. Section 2, how is energy transferred? So explain why a ceramic bowl will keep oatmeal hot longer than a stainless steel bowl. Well, if you don't know what a ceramic bowl is, a ceramic bowl is going to be more of an insulator. And why would you not want it in a stainless steel bowl? Well, stainless steel would be a type of metal, and metals are going to be pretty good conductors. So if you put hot oatmeal in a stainless steel bowl and you're holding it, you're going to feel that warmth very quickly. That heat from the oatmeal is going to transfer right through that metal and go into your hands and warm them up pretty quickly. It may not burn you depending on how hot your oatmeal is, but possibly. The ceramic bowl is going to act more like similar to a glass bowl or a plastic bowl or maybe even a styrofoam cup. It's an insulator, so that heat in your oatmeal is going to stay in your oatmeal. It's not going to work its way through that ceramic bowl. Number 2, explain which heat transfer method can take place if two objects at different temperatures are placed without touching each other in a vacuum. Hint, think about if hot air started at the bottom of a vacuum and cold air was at the top. All right. So what I'm getting at here is just if you have two different objects at two different temperatures without them touching, how is heat going to be transferred? Well, if nothing is touching and they're in a vacuum, it would have to be radiation, because radiation is the only way you're going to transfer heat when there's no medium or no matter around. And so radiation is your answer here. Number 3, define and provide an example of each of the following. So conduction, it's heat transfer by direct contact. Heat transfer by contact. An example of this would be frying up some bacon. You accidentally burn your hand as you're taking the cookies out of the oven. anything that involves directly touching it, or possibly putting your spoon in your oatmeal and all of a sudden you leave your spoon in that oatmeal for too long and you go back and grab it and it burns your hand. Well, maybe you have to add some sort of insulator on your spoon, like a little rubber handle or something like that. Convection, this is transferring heat by density differences. Typically you have something that gets warmed up and it becomes less dense, so it rises above the things around it that are more dense than it. And then as it rises, typically it's away from a heat source, so as it cools down, it condenses again and becomes more dense and sinks down. Then it gets close to that heat source again, expands and rises up and condenses and comes back down, and we call those convection currents. That's how wind is created. But lava lamps here, hot air balloon rising, air fryers circulating that hot air. This is also why your attic is going to be warmer than your basement typically, especially in this warm summer months. That warm air is rising. Radiation, heat transfer through, and this would be electromagnetic waves, or you can write EM waves. And what is an electromagnetic wave? Well, it is a wave that can travel through any sort of medium, and it doesn't even need a medium, meaning that it doesn't have to travel through solids, liquids, or gases. This is how the sun's warmth reaches us and the sun's light reaches us from all the way out there. It's going through space where at times there is no matter whatsoever to bounce off of, so it's just got to travel through space, through a vacuum, as we would say sometimes. But sitting by a campfire, feeling the warmth from it, or you are just walking outside and you get a suntan, you're feeling the warmth from the sun, that's radiation. Or a microwave cooks your food via radiation. Next one's number 4, state whether the scenario is conduction, convection, or radiation. Well, when you're frying 10 strips of bacon in a cast iron pan, everything is in direct contact. That is conduction. Feeling the warmth from sitting next to a fire, radiation. This method does not involve the movement of matter. So nothing is moving. This would be radiation. Radiation can travel through a vacuum. You don't need matter. Transfer of energy by the movements of fluids or gases with different temperatures. Remember, as something warms up, it rises, and it cools down and sinks. Those are convection currents. So convection is your answer there. Solar panels gather radiated energy from the sun. That is radiation. A fan is used to move heat throughout a home. Well, the fan is helping those convection currents move around. It's kind of an assisted convection, kind of like your air fryers have a fan going some of the times just to assist that air moving around, just so you're not always hot at the top and cool at the bottom. You have that air circulating. A lizard lies on a warm rock to stay warm. Well, the rock got warm likely because of radiation from the sun. And depending on what type of rock it is, it might hold that heat for a long period of time. So a lizard's going to go over there and lay on it and warm up. But the lizard's not warming up because of radiation. The lizard's in direct contact with the rock, so that is being warmed by conduction, or the heat is transferred from the rock directly to the lizard. Conduction. Energy transferred as electromagnetic waves. This is radiation. All right. Number 5, which ones are conductors, which ones are insulators? So conductors transfer heat easily or well, and insulators try to do the opposite. They want to resist that transfer. So a material that is a poor conductor of energy, like rubber, that'd be an insulator. A material that easily conducts heat or electricity, that is called a conductor. A metal spoon would be a conductor. Plastic fork, insulator. If you had a metal spoon and a plastic fork in boiling water, that metal spoon's going to warm up. The plastic fork probably is not going to warm up. It might even melt, but the plastic fork is not a conductor. It's an insulator. Marshmallow roaster or skewer. I should have given you a little more as to what the marshmallow roaster is made out of. Let's say it's metal. If it's metal, it's going to be a conductor. If you are using a wooden stick, that's an insulator. But a metal marshmallow roaster or skewer would be a conductor. Styrofoam cup is an insulator. That's why you put coffee in a styrofoam cup and not a metal cup. And then lastly, section 3, using heat. Apply what you have learned about cooling systems, heating and cooling systems, to determine which one's true and which one is false. So opening the door of your refrigerator will cool your kitchen. No, that's false. It might cool the air around it slightly, but you're not going to be able to cool your entire kitchen by opening up your refrigerator door. It's not going to be able to cool that much mass of air in your kitchen, so that one is false. Shivering when you warm up, or shivering when you're cold actually warms you up. That is true. Yes. You are shivering, you're increasing the energy of the molecules around you. So yes, you're increasing your temperature. Opening the door of the oven after turning it off. Obviously, don't turn it on and warm your kitchen. Don't want gas going through your house. But if you turn it off, yes, you can have your oven cracked and you can add some heat to your kitchen. Yes, that would work. That's true. Explain what happens when holding an ice cube for a long period of time. Where does the heat transfer? Well, we know heat transfers from hot to cold. So the warmth from your hand will go into the ice cube and melt it. You could slow that process by adding an insulator like a glove on your hand. If you're wearing a glove and you're holding the ice cube, it's going to slow down that heat transfer. So the ice cube will last a little longer. Specific heat is the energy required to raise the temperature of a substance a certain amount, typically by 1 degree. So something like water has a very high specific heat. It requires a lot of energy to change the temperature of it. That's why the ocean is similar temperatures all around the world. Obviously a little bit cooler in the polar regions, a little warmer near the tropics, but relatively the same. And then what would heat faster? A tar driveway or Bass Lake here in Underwood. That tar driveway would heat up much faster. Not only is the tar driveway black, so it's going to absorb much more radiation. Bass Lake's made of water, so it's going to reflect a lot of the radiation. But the tar also has a lower specific heat, so it's going to warm up much quicker. It's also a smaller mass. The tar driveway, much less mass. But even like a tarred parking lot out here, that's the word for it, tarred parking lot, even though that's still a large amount of mass, it's going to warm up much quicker than Bass Lake. And so that is your study guide. Let me know if you have any other questions.